Dr. Y. Sarada, Professor, Department of Mathematics, Anna University. Her area of specialization is applied probability and stochastic modeling. She has about 25 research publications in national and international journals. She has guided students for research projects. She has delivered lectures in her area of specialization in many institutions.
Welcome to the UGC lecture series on queuing and reliability. Presently, we are looking into the queuing models. As a quick recap, we were looking into the model 4 finite capacity multi-server model MMC GDN infinity when C is less than n. The arrival rate and the service rate were assumed to be lambda n equal to lambda when n lies between 0 and capital N, and mu n was defined as n mu if n lies between 0 and C, and as C mu if n lies between C and capital N. We considered the generalized Poisson queuing model, obtained the steady state probability of finding n customers in the system as Pn equal to rho power n by n factorial into P naught when n is between 0 and C, and rho power n by C factorial into C power n minus C into P naught when n lies between C and capital N, where rho is defined as lambda by mu. To find P naught, we use the normalizing condition sigma n equal to 0 to capital N, P n equal to 1, which gave P naught as the expression given here. We also found the performance measures LQ equal to rho power C plus 1 into P naught by C minus 1 factorial into C minus rho square into 1 minus rho by C whole power n minus C minus of n minus C times rho by C power capital N minus C into 1 minus rho by C when rho by C not equal to 1. If rho by C is equal to 1, we found LQ as P naught times rho power C into n minus C into n minus C plus 1 by C factorial into 2. Using the Little's formulae, we found the other performance measures Ls as LQ plus lambda effective by mu, Ws as Ls by lambda effective, and Wq equal to LQ by lambda effective, where lambda effective is lambda times 1 minus Pn, which is equal to mu times C minus C bar. So that Ls equal to now LQ plus C minus C bar, where the C bar is the expected number of idle servers, mathematically written as C bar equal to sigma n equal to 0 to C, C minus n into Pn. So that the Little's formulae can be rewritten as Ls equal to LQ plus lambda effective by mu, or W equal to LQ by lambda effective, which is rewritten as LQ by lambda into 1 minus Pn, so that Ls also equal to LQ plus lambda times 1 minus Pn by mu, and Ws equal to Ls by lambda times 1 minus Pn. We have replaced wherever lambda effective is there with lambda times 1 minus Pn. What is Pn? Pn is the probability that there are totally capital N customers in the system, so that the customers are lost. So, that is the probability of customers being lost, because we have placed a restriction on the capacity of the system to be capital N of them. So, now we will see the examples for this finite capacity multi-server model. The first example is a barber shop has 2 barbers and 3 chairs for customers. Assume that the customers arrive in Poisson fashion at a rate of 5 per hour, and that each barber services the customers according to an exponential distribution with mean 15 minutes. On arrival, if a customer finds that there are no empty chairs in the shop, he will leave. What is the expected number of customers in the shop? That is the question. So, we will just see the information given here. So, first of all, we have to decode what is the model given in the problem. So, it has been given that a barber shop, so that is the system, has 2 barbers. So, the number of servers is 2, C equal to 2, and there are 3 chairs for customers. Assume that the customers arrive in Poisson fashion at a rate of 5 per hour. So, the arrival rate has been given as 5 per hour, the unit is in hours, and that each barber services the customers according to an exponential distribution. So, the service times are exponential with the mean 15 minutes. So, what is the service rate then? 1 by mu has been given as 15 minutes. So, that mu equal to 1 by 15 per minute. So, the arrival rate we see it is 5 per hour, but the service rate is 1 by 15 per minute. So, in order to find rho, that is lambda by mu, we have to convert both the units to be uniform. So, either both should be in minutes or both should be in hours. So, on arrival, if a customer finds that there are no empty chairs in the shop, he will leave. So, this says that totally there are 3 chairs here. So, that if all the 3 chairs are full, then the newly arriving customer leaves the shop, leaves the system. So, there is a restriction on the capacity of the system. So, one more thing what we saw was the number of servers is 2 barbers are there, C equal to 2, and we saw that the arrivals are Poisson directly given here at a rate of 5 per hour. The service times are exponential, which indirectly tell us that the counting process associated with the number of customers departing is again Markovian or Poisson. So, this is C equal to 2, and the capacity there is a restriction. So, what is the question asked? Expected number of customers in the shop. So, we have to find L suffix capital S, LS is to be found. We will look into the solution. So, given C equal to 2, because only 2 barbers are there, the capacity is 3 because 3 chairs are there, and then lambda has been given as 5 per hour. So, we convert into minute as 5 by 60, which is equal to 1 by 12 customers per minute. Mu has been given as 1 by 15 per minute. So, now both lambda and mu are in terms of minutes. So, we can find rho, which is lambda by mu. So, that will be 15 by 12, which is nothing but 5 by 4. So, which is 1.25. So, you see that rho is not equal to 1, which is not required in the problem. What we need here is rho by C also to be less than 1 in general, because this is a finite capacity model. We have to just check whether rho by C is equal to 1 or not equal to 1. Why? Because accordingly we will use the P naught. So, now we have P naught to be written as sigma n equal to 0 to C minus 1. So, C equal to 2. So, we have 2 minus 1 rho power n by n factorial plus sigma n equal to C to capital N. C is what? 2 here, capital N is 3, and this is rho power n by C power n minus C into C factorial. So, rho power n by 2 power n minus 2 into 2 factorial, the whole inverse. Rho is nothing but 15 by 12, so which is 5 by 4, so 1.25. So, simplifying this, we have this value for P naught to be 0.28. Next, we will see what is LS. LS is given by LQ plus C minus P naught into sigma n equal to 0 to C minus 1, C minus n into rho power n by n factorial, rho is lambda by mu. So, substituting that LQ we see P3 plus 2 minus 3.2 into P naught after simplification. So, we have this value to be 1.226 customers. So, which is approximately we can make it to be 1 customer. So, the expected number of customers in the shop, that is LS, is approximately equal to 1 customer. So, that is what we have here. This is what we had to compute in the problem. One more example we will see. A 2-person barber shop has 5 chairs to accommodate for waiting customers. So, again 2-person barber shop again is the system, 2-person. So, number of servers involved are 2 here, has 5 chairs to accommodate the waiting customers. So, totally there are 5 chairs. So, capital N is equal to 5, plus you also have number of serving barbers, namely servers are 2. Potential customers who arriving when all 5 chairs are full leave without entering barber shop. So, this sentence tells us that there is a restriction on the capacity of the system. What it says is potential customers who arrive when all 5 chairs are full leave without entering the barber shop. Customers arrive at the average rate of 4 per hour and spend an average of 12 minutes in the barber's chair. The question is to compute P0, P1, P7, E of NQ and E of WS. So, we have to first decode the model here. Let us look into the Kendall's notation, the indices one by one. So, the Kendall's notation, we have first index is about the arrivals. So, the information given here is potential customers arrive when all the 5 chairs are full and they leave without entering the barber shop. Customers arrive at the average rate of 4 per hour. So, here this part tells us that the arrivals are Markovian and spend an average of 12 minutes in the barber's chair. So, the service time information has been given to be exponential. So, it means that the departure process is again Markovian. Number of servers C equal to 2, so MMC, and then we have about the restriction that capital N equal to 5 plus 2. 2 persons are serving. Apart from that, it says that there are 5 chairs to accommodate the waiting customers. So, which means that the customers who wait are maximum 5 plus 2 are to undergo service with the 2 barbers service. So, the total number of customers that can be accommodated in the shop is 7. So, hurriedly we may hastily write capital N equal to 5 because of this phrase, namely shop has 5 chairs, but it also says that to accommodate waiting customers. So, we have to take into account the 2 customers who are being served by the servers plus the 5 chairs which are in addition provided to the waiting customers. So, the capacity of the system capital N is equal to 7 and there is no restriction on the source. So, we have the model to be MMC GD N infinity. So, in the notation it is MM2 GD 7/infinity. So, these are the performance measures. The solution is given lambda equal to 4 per hour, mu equal to 5 per hour, C equal to 2, N equal to 7. P naught using the formula is sigma n equal to 0 to c minus 1. So, which is 2 minus 1 rho power n by n factorial, rho is lambda by mu, which would be 4 by 5 in this case. We have converted mu from minutes to hours. And then we have plus sigma n equal to 2 to 7, that is c to capital N, c is 2 and capital N is 7 here, into 1 by c power n minus c, that is 2 power n minus 2 into rho power n by c factorial. So, which is 2 factorial the whole inverse. As I said earlier, rho equal to lambda by mu, which is 4 divided by 5. So, that the units are uniformly given in terms of hours. So, we have rho equal to 4 by 5. After substituting and simplifying, P naught would be 0.4287. Next, we had to compute P1 and P7. So, the general formula Pn is given as following, namely Pn equal to rho power n by n factorial into P naught when n is less than c. So, c is 2 here, 0 less than or equal to n less than 2. So, we have Pn equal to 1 by n factorial 4 by 5 whole power n into 0.4287. When n lies between c and capital N equal to 7, c equal to 2 here, capital N equal to 7. So, we have written here n lying between 2 and 7. It is given by 1 by c power n minus c into c factorial. So, 2 power n minus 2 into 2 factorial into rho power n. So, this is nothing but 4 by 5 power n into P naught. P naught is 0.4287. So, putting n equal to 1. So, it falls into the first case. So, we have P1 equal to 0.3430. When n equal to 7, we use the second formula. So, which is given by 0.0014. We had to find LQ. So, which is given by 0.15 customers. In order to find LS, we have 0.95 customers. The formula used is LQ by LQ plus, using the Little's formula, we get LS here, which is obtained as 0.95 customers, and WS is again given by LS by lambda effective. So, we have 0.95 by lambda effective has been found as 3.1984. Lambda effective is lambda times 1 minus P7, Pn, which is P7 here. That is how you get lambda effective to be 3.1984. And so, we have Ws to be simplified as 0.2957 hours. If it is to be expressed in terms of minutes, we have Ws equal to 17.7 minutes. So, this is the information we had to compute P naught, P1, P7 and then W, S and LQ. Now, we will look into the exercise problems. Customers arrive at a clinic at the rate of 8 per hour, Poisson arrivals they are, and the doctor can serve at the rate of 9 per hour, which is exponential. There is a restriction of 10 people in the system. So, find the probability that the server is free. The probability that a person entering does not see a queue. So far what is that we have? Customers arrive at the clinic in a Poisson fashion. The rate has been given to you directly as 8 per hour. And the doctor can serve at the rate of 9 per hour, which is exponential. So, the service rate has been given as 9 per hour, which is also given directly here. And there is a restriction of 10 people in the system. So, the patients at most that can be accommodated in the clinic is 10. So, capital N has been given to be 10. and doctor, so it is only C equal to 1. So, we have the probability that the server is free, that is to be found. So, when is the doctor idle? Next question is the probability that a person entering does not see a queue. So, when will the person not see a queue? When the doctor is free, server should be free. So, you have to find that the probability that the server is idle. Next question is the probability of an entering person forced to leave the queue without joining it. So, when is this possible? When the system is full. And what is the capacity of the system? There can be only totally capital N equal to 10 patients in the clinic. So, once there are 10 patients in the clinic, then the system is full, clinic is full, and the newly arriving customer has to leave. So, the expected number in the system is the next question. So, performance measures are being asked here. So, which is nothing but LS, and the last question is the expected waiting time in the queue. So, this is nothing but WQ. Next exercise problem. People arrive at a web browsing center at the rate of 10 per hour, that is Poisson arrivals. There are 2 computers used for browsing and the expected time taken by a person is 10 minutes, namely service time is 10 minutes. There are 2 computers and that there are 5 additional chairs for waiting people to sit, and that people do not join the line if these chairs are full. So, from this you can decode what is the capacity of the system and how many servers are there, 2 computers are there. We will look into the questions now. Find the probability that both the computers are free when a person arrives. So, servers are 2 here. The probability that the person can use a computer immediately on arrival. So, when can a new arrival use the system? When there is one customer in the system or no customer in the system. Next question is the probability that there is no queue on arrival. So, once again it is possible that the servers are free and a new arrival directly goes for service. There is no queue in the system. Next question is the performance measure, the expected number in the system and the expected waiting time in the system. LS, expected number in the system, and expected waiting time in the system. So, WS are asked. The next question is the number of computers that should be made available if the expected waiting time in the queue is to be less than 10 minutes. So, it is again an additional question where it is asked that if the waiting time in the queue is to be less than 10 minutes, then how many servers should be made available in the system. The next question is the center can rent additional space to add 5 more chairs at a rent of rupees 150 per month. Assume that the center works for 30 days in a month and for 12 hours a day. Should they rent the space? That is the question. So, here cost factors are involved. Based on that we have to answer this question. Next we will see the model, namely infinite server model. So, in this case we have every customer is server himself or herself. So, in the Kendall's notation we have infinity, GD infinity infinity. So, the arrivals are Markovian, departures are Markovian, and C, the number of servers is infinite, queuing discipline is general, there is no restriction on either the capacity of the system or the source. The rates we assume here for this model are lambda n equal to lambda when n equal to 0, 1, 2 and so on, and mu n is assumed to be n times mu where n equal to 1, 2, 3 etc. As before, we have to consider the generalized Poisson queuing model, substitute for lambda n mu n in Pn and P naught and find the performance measures. Let us look into that. So, the generalized Poisson queuing model, we have, that is the notation wise, mn 1 gd infinity infinity. Pn was found as lambda naught, lambda 1, lambda 2 into lambda 3 and so on, lambda n minus 1 divided by mu 1, mu 2, mu 3 etc. mu n into P naught. Now, Pn is equal to rho power n by n factorial into P naught for this model when n equal to 0, 1, 2, 3 etc. and P naught has been found as e power minus rho. So, let us look into this. So, we have Pn equal to lambda naught, lambda 1 and so on, lambda n minus 1 divided by mu 1, mu 2 and so on, mu n into P naught. When n equal to 1, we have the rates to be lambda n was defined as lambda for all n and mu n was defined as n mu for all n. So, that now substitute these values Pn equal to lambda naught is lambda, lambda 1 is lambda and so on, lambda n minus 1 is lambda. Again, as before, we have total number of terms in the numerator are n divided by mu 1 is 1 into mu, mu 2 is 2 into mu and so on, mu n is n into mu into P naught. So, in the denominator also you have totally n mu's taken as a product and we have the numbers associated here are 1 into mu, 2 into mu, 3 into mu and so on, n into mu for the last term. So, we rewrite this as lambda power n by mu power n into 1 into 2 into 3 and so on up to n whole thing into P naught. So, this tantamounts to writing lambda by mu the whole power n by n factorial into P naught. When I write rho as lambda by mu, I have Pn equal to rho power n by n factorial into P naught where n equal to 0, 1, 2, 3 and so on. So, this is the expression we got for Pn rho power n by n factorial into P naught. Next, the problem is to find P naught using the normalizing condition. So, I want you to compute this expression for P naught using the normalizing condition, take it as an exercise. As a quick recap, what we saw today, we looked into the problems or the examples for the multi-server finite capacity Markovian queuing model and we just got started with the infinite server model or the self-service model. We obtained the probability of finding n customers in the system in the steady state. Thank you.